19, I want to ask a question. I want you to think, please, before you respond. How many of you think that you would have fared better, likely considerably so, on exam 1 if you would have had more time? Okay. Now, I personally am not at all happy with the assembly exam time slots that the university gives us, but I can't do anything to change that. What I can do, though, is to offer you, as a group, the opportunity, if as a group you would be of a mind to do this, take the remaining exams either on Saturday afternoon or Sunday afternoon. On Sunday afternoon, for example, I would gladly allow you to work on the same sort of exam with the same number of questions from 1 p.m. to 5 p.m. if you want it. Now, I've asked questions like this in the past and never as yet have really done so. But I got a strong feeling that one of the difficulties with this multiple choice exam format is time restriction. And I don't want time restriction. I don't mind giving you all the time necessary for you to be able to demonstrate what you know. So, unless you have a legitimate conflict, how many would go for Sunday exam? I'm asking. Now keep in mind, I do not accept as a legitimate conflict the desire to watch sports on TV. I'm just asking. We'll talk further about this. How about Saturday? Now, I know that some of you may have real conflicts, like you may have to work. And if you're in a situation like that, I'd be glad to accommodate you on an individual basis, provided there are not too many folks who would require such accommodations. But keep what I just asked you to think about in mind, and we'll talk more about this. We got a lot of time to talk about it. Now, last time, given that we have now laid the foundation for being able to deal with the complete detailed analysis of any water solution, so as to find as necessary the concentration of every species in the pot whose existence depends on pH. We looked last time at calculation of the hydronium ion concentration for 10th molar to 2 sig fig sodium bicarb solution. Found out that's a challenging case. Main BLABEQ, acid-base equilibrium, is between bicarb ions. So you had to go further than this main BL acid-base EQ. And in so doing, since we looked at this last time in fairly great detail, and the total solution of such is in the notes, recognize that you wind up with a system that's got multiple unknowns. So you need to apply material balance and charge balance. But after you realize what you need to apply, the corresponding algebra is really not difficult at all. What counts is to realize what you need to apply and understand how to apply it. Again, the complete analysis of that situation, of that system, pardon me, is in the notes. And you wind up finding out, given that we started by knowing that the sodium bicarb solution is mildly basic, that the hydronium ion concentration got to be less than 1.0 times 10 to the minus 7. Here, in fact, is the hydronium ion concentration for the 10th molar sodium bicarb solution. So, by way of what's in the notes, we next extend this consideration to ask, how about calculating the hydronium ion concentration for 0.10 molar ammonium bicarb solution, which we talked about in brief at the conclusion of our last chat. We find that this solution is also mildly basic because Kb bicarb ion, with bicarb being the strongest base in high concentration in the system, is larger than Ka ammonium ion, with ammonium ion being the strongest acid that's present in this system at high concentration. But since ammonium ion is a somewhat stronger Bronsted acid than bicarb ion, we find out that even though this solution is mildly basic, like the sodium bicarb solution, this is less mildly basic than this solution. So the hydronium ion concentration for 0.10 molar ammonium bicarb solution has got to compare how to 4.5 times 10 to the minus 10. Pardon me. Got to be greater, but still less than 1.0 times 10 to the minus 7. So if we were to set about the task of actually doing the calculation, we'd have to write material balance and charge balance relationships. And you could pay attention to Ka ammonium ion or Kb bicarb ion. It wouldn't make any difference. Either provide a handle on the pH. One gives you the hydronium ion molarity, and Kb bicarb gives you the hydroxide ion molarity. Hydronium ion molarity, of course, coming from Ka ammonium ion. So, in parallel to the way we tackled, or the way I tackled the calculation for the hydronium ion concentration for the sodium bicarb solution, which again is outlined in detail in the notes, where I found the boundary values for the hydronium ion concentration. So I have an idea of what kind of hydronium ion concentration I want to start with as a test value. Notice this method of solution very much parallels what I did with this speculation on percent ionization. We got this hydronium ion concentration in the box, in the first case for the sodium bicarb solution. So we'll try a value for the hydronium ion concentration that's halfway between hydronium ion min and hydronium ion max. And then I'll know which way, if that isn't the answer, I'll know which way to adjust my next trial value for the hydronium ion concentration. So in this case, for the ammonium bicarb solution, I'll take advantage of what I found by getting the hydronium ion concentration for the sodium bicarb solution and use these as my boundary values. Because as we have just recognized, the hydronium ion concentration for the ammonium bicarb solution has got to be bigger than this value, which is hydronium ion concentration for the sodium bicarb solution, because this system is less basic than this system. But again, since this system is also mildly basic, the hydronium ion concentration max has got to be 1.0 times 10 to the minus 7. So, there's the box. Hydronium ion concentration for the ammonium bicarb solution, which I know before I do any calculations, any dealing with MB, CB, and equilibrium constant considerations and the like, is a number smaller than this but bigger than this. So just as I did with sodium bicarb solution, I'll take pH 7.00 and the pH for this. What's the gee whiz pH for this? Now the pH for that is 9 less the log of 4.5. What's the gee whiz log of 4.5? Roughly, log of 4 is 0.6 and log of 5 is 0.7. I mean, it's valuable to keep this stuff in your noggin. Immediately gets you in the ball game. So, 0.65, something like that. Now I'm treating it linearly. So I know that the upper limit pH is going to be about 8.35, 8.34, something like that. So I'll pick me a pH that's halfway between those two values, and that's what I'm going to start with. Now, if you want to tackle this calculation just for practice, I believe the actual pH for the ammonium bicarb solution is given. I think I got it there. I think it's 7.85. Yeah. Now, a comment on problem 18.2. When I first thought about this and wrote these notes, I mean the present form of these notes about 4 years ago. Maybe 5, I don't know. If we are assigned the task of calculating the hydronium ion concentration, pH for this solution, we start by realizing that the principal acid-base equilibrium again doesn't involve hydronium ion or hydroxide ion. So we're going to have to look at, to get pH for this system, at what? What K values would we have available to get at pH for this system? Now, perhaps you also recall that one of the headaches associated with this system is that we cannot, when we write the charge balance equation for this system, which is hydronium ion molarity plus ammonium ion molarity equals cyanide ion molarity plus hydroxide ion molarity, we can't immediately set that equal to a charge sum, because this reaction makes substantial progress left to right before equilibrium is achieved, as indicated by this K value. Given the amount of time we've spent dealing with K values, have you recognized now, from an extent standpoint, what a K value of 1 means? What's that mean? A given reaction, left to right, has a K value of 1. What's that mean? To what extent the reaction proceed? 50%. That's what it means. The K value is 1. The equilibrium molarity of products divided by the equilibrium molarity of reactants, 1. They're equal. So you had to go left to right 50%. And that's an appreciable extent. Okay. Well, that means at the minimum that in our ammonium cyanide solution, we really have, beside water, 4 principal species, don't we? This, they're all principal species in there. So, to get my arithmetic handle on pH, Can I use Ka ammonium ion? Hell yes. Can I use Kb cyanide ion? Hell yes. KHCN. Hell yes. KBH3N. Every one of them. Doesn't matter. Because I'm dealing with equilibrium constants, each of which give me a handle on pH, and each of which corresponds to a principal species in the system. And all these remarks that I'm making to you follow from our knowledge of what property of this system. What do we have to pay attention to first in any chemical system? We're going to do something with it. Inventory. Right? Hey, that's where it's at. No inventory, you lose. Because you have no chance to win. What else could you do but lose? If you know what you're dealing with, now you got a chance to win. Now then, problem 18.2, as it is stated in these notes, has an incorrect qualification. I did a gee whiz arithmetic on this about maybe 15 minutes ago. I said, uh-oh. As it is stated in the notes, problem 18.2 says this calculation is easy. The reason why I made that statement is when I first considered this equilibrium some years ago, after having recognized that K for this is appreciable, whereas K for ammonium ion is 5.6 times 10 to the minus 10, Ka, and Kb cyanide ion is 1.6 times 10 to the minus 5. You know how to get the value. I said, heck, those K values are nothing compared to this, and that's true. So I said, since I know K, and by now you ought to know how to calculate K for this. If not, we'll, in a few minutes, spend more time in detail on calculating K for an equilibrium reaction for which K is not provided. Okay? So, I said this. Notice I told you I'm going to put this thing on bonus quiz 2, and I'm now laying foundation for your ability to tackle this successfully. Give you an opportunity to do something that students very much like to do. Get points. Get 10 points. Student money. That's points. I found out long ago, when I got into this business called teaching, that when I jump up and down and holler about students not paying attention, correctly so, to significant figures, things like that, but don't take off any points, they don't care what the hell I said. They don't care how much I hollered and screamed and cussed. But as soon as I take off points, then they pay attention. Okay. So, I'm giving you the opportunity here to get the points. NC minus. I'm sorry, but this thing is here and I can't rip it off. Okay? I wrote for this. Remember what I said? Given that K for this is large, Ka 5.6 times 10 to the minus 10. Right from the table. Kb, again, really right from the table, but you're just using Ka HCN to calculate such. I said, heck, this K is very large compared to these. So the ionization extent of cyanide ion by reaction with water compared to this reaction is nothing. The ionization extent of ammonium ion, nothing. So I said, let's do this. Because these molarities ought to be equal, which means these molarities have to be equal. And now with the arithmetic I did today, I'm going to put quotes on that, because this is not quite true. And that leads to the bug in the statement of this problem as it is in the notes. So I'm telling you what you have to pay attention to wrestle with this. I don't know exactly as yet how I'll state this question, because you have not even yet reached the time during this term when you got to turn in bonus quiz 1.
You said that that's not true.
That's right, that's not true. It's close to true, but it's not true.
Because the HCF and H3 are not equal.
Well, what I'm telling you is the molarity of this is not quite the same as the molarity of this. And the molarity of this is not quite the same as the molarity of this. And the numerical significance of this will be found in solving this correctly. So on bonus quiz 2, I'm going to ask you to solve this correctly and ask you to tell me why this isn't true. Tell me why these molarities are not equal, and why these molarities are not equal. It comes as a consequence of understanding these K values and what they mean. Enough said on that. And now let's wrap up chapter 18 with one final problem. Let's imagine we have the task of calculating the hydronium ion concentration for this very dilute solution of ammonium sulfate. Recognizing, among other things, for example, that the initial molarity of ammonium ion is 1.0 times 10 to the minus 5. And sulfate ion, of course. (5.0 times 10 to the minus 6). Sub I, initial molarity. So our principal system inventory initially is on the board. Now, with the exception of water. Main species ammonium ion, sulfate ion, and water. And this again is another system parallel to the couple system we've just been discussing, where the principal acid-base equilibrium is not a hydroxide ion or hydronium ion producing equilibrium. Here it is. K value for this equilibrium is 4.7 times 10 to the minus 8. So does it appear that for this system, as for example parallel to this ammonium cyanide system we looked at a moment ago, you think it's possible for this system, when we write the charge balance equation, we can immediately set it equal to a charge sum? Does this reaction proceed to an extent where you're going to wind up with an appreciable molarity of this and this compared to these molarities? Now then, how do I get a handle on the maximum molarity for hydronium ion, given that this solution, before I do any arithmetic, is known to be mildly what? Acidic or basic? Acidic. Because Ka ammonium ion is 5.6 times 10 to the minus 10. And Kb sulfate ion, which you know how to calculate if you don't remember it, is 8.3 times 10 to the minus 13. And I've got twice as many moles, at least initially, of ammonium ion as I have sulfate ion in the pot. So clearly the system is going to be mildly acidic, because the molarity of ammonium ion is considerably greater than the molarity of sulfate ion, and Ka ammonium ion is a hell of a lot greater than Kb sulfate ion. So I know the pot is mildly acidic. So, in parallel to what we've done with these earlier considerations, let's try to get a handle on the hydronium ion concentration max. Here's M sub I for ammonium ion, Ka ammonium ion. You've seen this game before. We're taking ammonium ion plus water, products, hydronium ion and ammonia, and applying to that x squared over M sub I minus x. And neglecting x in the denominator. To get, based on the initial molarity of ammonium ion, a handle on, quote unquote, on the hydronium ion concentration max. Well, this gives 7.5 times 10 to the minus 8. You can do the arithmetic as necessary. So is this possible? How can we immediately rule this out as any value which is even close to the correct hydronium ion concentration for the solution? The solution is acidic, damn it. The hydronium ion concentration is at least 1 times 10 to the minus 7. So that can't be right. Now let's pay attention to max percent ionization of ammonium ion as a function of dilution, given that this solution is pretty damn dilute. Remember the recipe? It's Ka for the acid, if you had a base, it'd be Kb, times 100% divided by Ka plus 1.0 times 10 to the minus 7. Here it is, I get 0.56%. So I'll take 0.56% of 1.0 times 10 to the minus 5. That's our initial molarity of ammonium ion. And I get 5.6 times 10 to the minus 8. Ha ha! That even gives me a smaller number than this. So what's this stuff mean? In regard to correctly calculating the hydronium ion concentration for this solution. What's this information mean? Let me be more blunt. Have we now established that I cannot get the correct hydronium ion concentration for this solution by simply paying attention to the presence of ammonium ion? Well then, what else do we have to pay attention to? Water! You betcha. Kw is part of this puzzle. It was not part of the previous puzzles, but it's part of this puzzle. All right? Now then, what about sulfate ion? Do you think in this system the presence of sulfate ion will exert any measurable impact on the solution hydronium ion concentration? No. Not only is its K value very tiny next to that of ammonium ion, it's only present at a molarity of 5.6 times 10 to the 5.0 times 10 to the minus 6. And when we revisit the molarity of ammonium ion, the initial molarity of ammonium ion, which is 1.0 times 10 to the minus 5, based on our hydronium ion max approximations, based strictly on the presence of ammonium ion, we already realize, hey, you got to pay attention to water in this pot. True, water is a much weaker acid. But water in this pot is sure as hell present at a concentration which grossly outnumbers that of ammonium ion as well as sulfate ion. Practically speaking, in this pot, the water molarity is 55.5. It's like pure water. I mean, this stuff is so dilute that the solute will not occupy any volume of consequence in the overall solution. All right, let's write the material balance statements. Everybody write these? Charge balance. Everybody write this? Can we set this equal to a charge sum? If so, what is that charge sum? Do we start by knowing that even though this solution is mild, even though this is acidic, it's very mildly so? That means the hydronium ion concentration for this solution will be very close to or considerably far from 1.0 times 10 to the minus 7. How do you vote? Close to or far from? We've looked at the magnitude of impact on a max basis on the hydronium ion concentration for the system by the main solute acid and find out that this isn't much. Remember? These hydronium ion molarities based on the presence of ammonium ion, each of which found to be less than 1.0 times 10 to the minus 7, which told us we got to go look at water and what it's doing in this pot. And since we know the system is mildly acidic, how will the contribution to the solution hydronium ion concentration for this system by autoionization of water, how will the contribution to the system hydronium ion concentration by ionization of water compare to 1.0 times 10 to the minus 7? You remember when we played this game for very dilute sodium hydroxide solution, very dilute hydrochloric acid solution? In the very dilute hydrochloric acid solution, the one that's in the notes 3 times 10 to the minus 8 molar. We start by realizing that can't be the solution concentration of hydronium ion, because that would say this acidic solution is basic. So that told us we had to pay attention to Kw. So we knew the hydronium ion concentration for that solution was the sum of the molarity contribution made by HCl, which was 3 times 10 to the minus 8 moles per liter, plus the contribution made by water plus water. How did that compare to 1.0 times 10 to the minus 7? If I have this equilibrium existing in pure water, good stuff. There it is in my cup. Well, it's really tap water. The ionized water is pretty flat. Hasn't got any flavoring agents in it. Let's imagine this is deionized water. In the ionized water, hydronium ion molarity, hydroxide ion molarities are the same, and at NLC, 1.0 times 10 to the minus 7. Just saying things with which we all have knowledge. I repeat, in an acidic solution, like 3 times 10 to the minus 8 molar HCl, can the autoionization of water make a contribution to the hydronium ion molarity as large as 1.0 times 10 to the minus 7? Yes or no? Here's this equilibrium. It's living in my pot. I add an external source of hydronium ion. Right? That's what happens in 3 times 10 to the minus 8 molar HCl solution. That's what happens in this solution. Because I know this solution is mildly acidic. What impact does the addition of hydronium ion have on this equilibrium? At the instant at which I add the hydronium ion, Le Chatelier, one of these got to go to get me back to equilibrium. Right to left or left to right? Which way is it going to go? Right to left. So I repeat my question. In this mildly acidic solution, is it possible that the contribution to the hydronium ion concentration by the autoionization of water is as large as 1.0 times 10 to the minus 7? No! Can't be. We're letting this stuff talk to us. Now I know this is difficult. That's why I have great sympathy for you. But this is where it's at. Understanding what this chemistry means. Because when you understand what the chemistry means, you can do the arithmetic. When we don't understand what the chemistry means, the arithmetic is meaningless. So if I take this and add 1.0 times 10 to the minus 7 to it, because this solution is mildly acidic, so the upper limit contribution to the hydronium ion molarity by the autoionization of water is 1.0 times 10 to the minus 7. In fact, it's going to be a little bit less than that. So if I add 1.0 times 10 to the minus 7 to this, what's that going to give me? What will be the significance of that value in this system? It won't be the hydronium ion concentration for the system, but it will be the upper limit value for the hydronium ion concentration. I'll know the hydronium ion concentration for the pods has got to be smaller than that value, yet equal to or bigger than 1.0 times 10 to the minus 7. So all that chat was about, or not exclusively, but all that chat laid foundation for recognizing that for this system, can I set the charge balance equation equal to a charge sum? And if so, what's the charge sum? You never had to think about numbers like this before, have you? That's what you got to do in science class. It's all right. We'll take our time. We'll go along with this patiently. You agree with this? We know the hydronium ion concentration cannot be as big as this plus this. And the sum of these numbers compares how to this number? It's a good deal smaller, isn't it? So, this should be legitimate. Now, what I want you to do, because we provided the analysis of the chemistry of the system, to the extent that you should now know how to tackle this issue. Let me give you one more thing, and that is To calculate the hydronium ion concentration for this system, I chose to use Ka ammonium ion. And there it is chemically. This is what I want. So what am I going to do with my material balance and charge balance expressions? I'm going to solve them for each of these in terms of what? Hydronium ion concentration. I'm going to put them in there, and then I got one equation and one unknown. That's what I'm going to do. So here's my directive for you to have a happy weekend. Do it! We'll pick it up from that point on Monday.